Hey everyone, and welcome back to another AP Calculus video. Today we're going to extend what we talked about with differential equations one more step. And instead of calling it solving a differential equation and saying, hey, we're starting with a derivative, where did it come from, and finding the antiderivative, we're now going to start this process of finding something called the indefinite integral. And essentially, it's the same process that we use to solve a differential equation. We're just calling the equation something different. So instead of saying, here's the derivative, where did it come from? Now we're saying, here's a function, find the antiderivative. And the process that we use to find that antiderivative is called integration. And there's a couple different techniques that we can use to integrate, that's the verb that we use, and to solve a differential equation or whatever. But basically what I want you to understand is that this is an extension of what we talked about when we discussed differential equations in the first lesson there. So what is the indefinite integral? Well, we've talked about the definite integral, referring to the area under a curve. Anytime we have limits of integration, the upper limit and the lower limit, we're talking about finding the antiderivative, evaluating that, and applying it in terms of like finding the area under a curve. And oftentimes, we're given a rate, we integrate, it tells us the amount of change. That's kind of what we talked about in the previous unit with regard to the definite integral. The indefinite integral is simply an antiderivative, and it takes into account the fact that there's an infinite number of solutions to every integral or to every differential equation, depending on what you're starting with, that all differ by a constant. And so the whole idea here is that sometimes we're given information about the original function or the antiderivative, depending on what problem you're solving. And if we're given initial conditions, then we can find that constant. But if we can't find the initial conditions, then we have to respect the fact that there could be a constant there. We don't know what it is, and we have to represent it every single time with a plus c. So let's look at some of this notation. The indefinite integral is an integral with no limits of integration. And essentially, you're finding the antiderivative. So here's an example. We're going to start with this one, x squared minus sine x. And one of the cool things about integration is that just like when we do a derivative, we can do what's called term-by-term integration. And really, we can think of this, and you don't need to write it this way every time, but we can think of this as the integral of x squared dx minus the integral of sine x dx. So this allows us to basically integrate each term independently from the others anytime there's addition or subtraction. So the antiderivative of each term is going to be the solution. So where did x squared come from? It came from x cubed over 3. Where did sine come from? Well, we always remember we have this wheel of signs, sine, cosine, negative cosine. The derivatives are all clockwise, but the antiderivatives are all anti-clockwise or counterclockwise. So where did sine come from? Sine came from negative cosine. So I'm going to have minus negative cosine. Well, those are going to cancel each other out, turn to a plus. You could have also thought of it as a negative sign, and you would have gotten to the same result. And then plus c. So when I clean this up, the function, the solution, capital F of x, is x cubed over 3 plus cosine of x plus c. And you can always check to see if you take the derivative of your answer, does it get you back to where you started from? That's always an excellent, little mental check is, am I getting the right answer? Am I getting back to where I started from? So now let's kind of talk a little bit about some of the properties of integrals. And this might be a great place to kind of pause and do some copying when it comes to the notes. But these are the properties of indefinite integrals, and essentially they're the same as definite integrals. So they should make a lot of sense. So the first one says anytime we have a constant, we can factor the constant out. That's a really useful thing because later on in the next unit after this one, in Unit 7, for us, we're going to be discussing some applications of integrals, and we're going to need to remember to pull out a constant. And pi will be lurking around quite a bit in that particular application. Number 2 says you can take basically one integrand that is added or subtracted. You can split them up into terms and make 2 separate integrals. Number 3 is all about the idea of that exponent and how do you deal with the exponent. We've been doing a lot of these over and over and over again. you have this one here, number 4, u to the negative 1 is the same as 1 over u. And the antiderivative is the natural log of the absolute value of u. And in the first video, when we did the differential equation solutions, I talked a little bit about why the natural log needs those absolute value bars, and it has to do with the domain of the original function. When we start with 1 over x, the domain is all real numbers. Well, natural log has a domain of x needing to be greater than 0. So you need to account for the fact that in the original function, x could be negative. And in the derivative, the domain of the derivative is the same as the domain of the original function. So by putting absolute value bars, the domain stays the same, and we also account for the fact that natural log can only take positive values. Number 5, e to the u, the derivative is just itself, so the integral is just itself, or the antiderivative. Number 6 is one we're actually going to learn where this comes from, and we're going to do a proof of it later on. That's a BC topic that we talk about in Calculus BC. So for the BC lessons, we'll be doing a proof of number 6 here. But for the rest of us, we can just jot it down for now. Number 7, number 8, these are all pretty straightforward. I'll be honest, number 7 I've never used before, so don't stress too much about it. And then here are our trig functions. And remember, you can do these trig functions using that wheel of signs. So a couple little tricks, you've got sine, negative sine, cosine, negative cosine, and we just saw this. The derivatives go clockwise. The antiderivatives go counterclockwise. Okay, so that's where those are going to come from, and that's a good way to remember your sines and cosines. Now we can also deal with tangent and secant and cosecant and all those by remembering our little pst mnemonic, right? So PSST. So for the derivatives, you go inwards, right? So the derivative of tangent is secant secant, or secant squared. The derivative of secant is secant tangent. Easy enough. And then you can also remember it by using the cofunctions. We just need to remember there's a negative sign in there. So we have cosecant, cosecant, and cotangent. And so the derivative of cotangent is negative cosecant squared, because it's negative cosecant, cosecant. And then the derivative of cosecant is negative cosecant cotangent. So if we can remember this little mnemonic for finding the derivatives, we just reverse it for finding the antiderivatives. So you can see secant squared came from tangent. So that's where that derivative and that antiderivative is going to come from. So use those mnemonics, because on your AP exam, you're not going to have this list of formulas. And so this kind of rounds it out. If you want to pause and jot them down, you can. It's always nice to have a formula sheet handy, and there will be one provided, at least in the beginning, to my students to be able to use on things. But just know there's coming a day when you can't have it, and we'll be slowly doing away with those formula sheets. So let's talk about what happens when we don't have a nice, obvious integral. One of the trickiest things that a lot of students have trouble with is, as we learn various integration techniques, they don't know which one to apply. So the first thing you're always going to do is you're always going to look and run through the list of possible formulas in your mind. So this little list here, you're going to run through it and you're going to say, well, is it an exponential function? Is it a logarithmic function? Is it a trig function? Is it just a power function, x to the 5th power or something like that, where I can find the antiderivative easily? That's step 1. Step 2 is what you have when you have two things that are often multiplied together, or when you have a function inside of another function. And so when you don't have a nice integral, when it's not obvious, and when you look at the integral and you would apply the chain rule to get the derivative, that's when we need to use this technique that we're going to learn here today called U-Substitution. And so when we don't have a nice integral, when we have stuff inside a function inside of another function, or when we notice that there's two functions multiplied together that look related in terms of their derivatives, this is when we're going to use this process called U-Substitution. And as we learn more techniques, and especially in Calc BC, we're going to be learning additional techniques. I'll be making a list for you when we learn those BC techniques, to be able to kind of go through a checklist. Is it this? Is it this? Is it this? And then it'll help you determine which integration technique to apply. So let's talk about this. When I have stuff inside, so let's zoom in on this example here. The integral of x plus 2 to the 5th power. Let's recall that the chain rule says that if I have stuff to a power, when I find that derivative, so if I were to have like 2x to the 10th power, the derivative would be 10 times 2x to the 9th. So I'd do that derivative, but then I'd have to tack on the derivative of the 2x, the chain rule. It's because I have a function inside of my function. Well, over here, that's what's happening. I have a function inside my function. And so the technique that we're going to use with this U-substitution, it makes it simpler. It says, well, let me take that inside function. I'm going to call it U, okay? So we're going to begin, and I'm going to tell you what U is. And as we progress, you are going to figure out what U will be and be able to integrate and be successful at it. So I'm going to rewrite this. I'm going to say U is x plus 2. So it's the stuff on the inside. So now I'm going to rewrite this as U to the 5th. The problem is I have to replace everything that has an x in it with something involving U. So this dx, I have to find its equivalent. And the way that I do that is I take this U equals x plus 2 and I find the derivative, du dx. Oh, it's just 1. So then what I'm going to do is I'm going to take this dx and I'm going to multiply it over here. So du is 1 times dx. In other words, du is just dx. So here I can take dx and I can replace it with du. The whole goal is to replace the stuff with u, and then whatever's left, if U-substitution is the appropriate technique, whatever's left, I should be able to replace with du. So now we just integrate this simple function. So here's what it looks like. The integral of u to the 5th is just u to the 6th over 6 plus c. Now I'm not quite done because I need to replace u with its original function. Remember, this is all the middle stuff. We don't want a final answer with u in it. So I'm going to replace it like this, and it's going to look like this. X plus 2 to the 6th over 6 plus c. And there's my answer. And that's what I'll be looking for. And that's how we're going to solve these integrals using this U-substitution. So let's try another one here. So I'm going to rewrite this function immediately the same way that I would with a derivative. Is I'm going to rewrite it like this. I'm going to say 4x minus 1 to the 1/2 power dx. So I'm going to get rid of the square root. Now, here, u is going to be 4x minus 1. So the first thing I'm going to do is I'm going to rewrite this, and I'm going to replace u to the 1/2. But now I need to get rid of dx, and I can't just replace it with du, and here's why. If I do du dx, the derivative of the u function, it is 4. So du is 4 times dx. Ooh. So I don't have a 4 floating around in here. So what I'm going to do is I'm going to solve for whatever dx is equal to. So I'm going to divide out the 4. So 1/4 du equals dx. So now this is what I'm going to replace dx with. Now I have a number in there, and it has to do with that chain rule. We're undoing the chain rule. That's the whole process of U-substitution. We have to find an equivalent form of dx in terms of du before we can find that antiderivative. So I'm going to go ahead and rewrite that. dx is just going to be 1/4 du. Now here's where the pulling out the constant is going to be really helpful and make me happy. I'm going to pull the constant out, and now I have u to the 1/2 du. And now I have a much easier function to find the integral of. So I'm going to keep the 1/4 out here, and then u to the 1/2, I'm going to add 1 and divide by the new power plus c. And I'm going to deal with my 3 halves there. So this becomes 1/4 times 2/3 u to the 3/2 plus c, which is 2 over 12 or 1/6. Let's replace u. U was 4x minus 1 to the 3/2 plus c. Whew. So capital F of x, we'll just use that antiderivative notation. So there you go. Now that's not too bad when we're solving for these. This is the process of U-substitution. We have to solve for dx and figure out what can we replace it with so that it has du there, so that we want to do an even swap, right? So dx is equivalent to 1/4 du, so we have to swap it out. We can't just replace dx with du. We have to find an equivalent. And it really depends. Each function is going to be different. So let's try this next one here. And if you want to pause and see if you can figure out what to use for u, go for it. But for me, I'm going to keep on rolling, and I'm going to remember that u should be whatever function is on the inside. So if there's an inner function, that's what I'm going to let u be. And so hopefully you are zoning in on this function right here. That is what I'm going to let u be. So I'm going to go ahead and rewrite it as the integral of cosine of u. Now I need to replace dx. So I'm going to find du dx equals 7. So du is 7 dx. But I don't have any 7s in there, so I'm going to divide the 7 over. 1/7 du equals dx. And this is what I'm going to replace dx with. It's its equivalent, so I'm going to trade it out. So times 1/7 du. I'm going to move the 1/7 to the outside and keep on going. All right, so the antiderivative of cosine is just sine. So this one's nice and easy. 1/7 times the sine of u plus c, and when I replace the u, 7x plus 5 plus c, there is my final answer. So in general, there is a little rule for this, maybe floating around up in that list of antiderivatives, but in general, there are some formulas that if you have the sine or the cosine of some sort of linear function in there, it's real easy. If you have a k, whatever k is, kx, you're just going to have the antiderivative divided by that constant. In this case, it was 7. So there are some formulas out there. I don't like them because they're very specific. I would rather just do U-substitution every time and get really good at that. Because really, in actuality, those formulas that try to make it easier came from U-substitution. So why not just go to the source, right? All right, so let's take a look at this one. We're going to use U-substitution, and the reason I'm going to use U-substitution is because I see I have things multiplied. I see I have a function inside of my function. E to the x is my original function, or is my outer function, and I have a cosine inside of the e. So I have stuff inside of a function. Cosine is my stuff. So when I try to decide what is going to be my u, I want to start with the stuff, okay? And I know that I need to use something other than just a formula because I have two functions multiplied together. If I have two functions that are added together, well, then I should look back to my formula sheet and see, is this one of those easier scenarios where I just pull the antiderivative from my formula sheet? Here they're multiplied. That's an indicator that I need something more. And U-substitution is what we have right now. So I'm going to let u be cosine of x. And before I even rewrite this, I'm going to just get in the habit of finding du. The derivative of cosine of x is negative sine of x dx. I just started moving the dx over. And so that's helpful to me because when I start to rewrite this integral, I'm going to have e to the u, but this sine, I have sine of x dx left. And notice when I found du, I had sine of x dx. So this is a little bit different. The negative I need to move over, but negative du is sine x dx. This is nice because if whatever I have left in my function, I need to be able to replace that with my du. So my goal is to get whatever's left. If it's dx, then what is dx equivalent to? If it's sine x dx, like we have here, what is that equivalent to? And what I can do is I can trade the sine x dx out for a negative du. So when I rewrite this integral, it's just e to the u times negative du. I'll pull the negative out, And by golly, it's just negative e to the u plus c. And when I replace u, negative e to the cosine of x plus c. There's my final answer. So it gets a little trickier when we start to have bigger functions more than just a number. Because the whole goal is to say, okay, I have my substitution, e to the cosine x becomes e to the u. I have a sine x and a dx left. What can I replace that with to turn everything into u's? So let's keep going. Here's another example. And again, the tricky part becomes, what do I allow u to be? What is the stuff that I'm going to replace? And so here, I'm going to look for the function inside of the function. And I have a power function here being squared, so it makes sense that I should attempt to let the inside stuff that's being raised to that power, that I'm going to start with, that I'm going to allow it to be u. Now, there are times when you say, well, I'm going to try u being this, and I can't get a replacement, right? So if you try U-substitution with one part of the function, and it doesn't work, you're not able to replace things, you still have an x floating around inside your integral, then maybe you're picking the wrong thing for u. But 99 times out of 100, if you can recognize what the stuff inside the function is, that's what you should use for your U-substitution. And again, I know this is a U-substitution problem because it's being multiplied. I can't simply, find the antiderivative. Now, side note, could I multiply it all out, turn it into one giant polynomial, and antiderivative that? Absolutely. That would be legit. It would just take a long time. This is a little bit faster. And the better we get at U-substitution, the more efficient we're going to become. So I'm going to start out, I'm going to let u be the x squared plus 2x minus 3, which means du is going to be 2x plus 2 dx. Okay, I'm getting there. Okay, so now when I rewrite this, it's going to be u squared, but my trouble is I have this x plus 1 dx to get rid of. So what's left? Well, when I found du, I have 2x plus 2, and I have a dx. Now these look similar, but they're not exactly the same. So I've got to do one little thing. I notice that I have a common factor here of 2. So I'm going to go ahead and rewrite this as 2 and then x plus 1. So now here's the cool part. There's what I have left in the function, the x plus 1 dx. That's what I need to replace. So I'm going to get that by itself. I'm going to divide by the 2, and I'm going to get 1/2 du equals x plus 1 dx. Well, now this is what I'm going to trade out. That's what I'm going to replace my x plus 1 dx with. So 1/2 du, I'm going to move the 1/2 to the outside. And 1/2 u cubed over 3 plus c. So now I'm going to get u, what was u again? X squared plus 2x minus 3. So I'm going to have x squared plus 2x minus 3 cubed all over 6 plus c. Whew. There's my answer. Okay? Now, could you have multiplied it out and done it a different way without U-substitution? Absolutely. Would it have taken a lot longer? Absolutely. Are some of you going to get to a point where you don't need to write down these middle steps and you'll see the chain rule play out backwards in your head? Absolutely. There's quite a few of you who will do that, and that's great. My recommendation to you is that if you use U-substitution, especially on an exam, a test, an AP exam, is that you show any middle steps. The reason why I caution you against just letting it play out in your head is because your grader, who's trying to score you, wants to make sure you understand the process, and you have to show some sort of middle steps. You can't just jump to the answer. You have to show your thinking. You're being scored not just on whether can you get to the answer or not, but you're thinking along the way. We want to make sure that you're accurate and mathematically sound. So as you practice this U-substitution, it is a tricky thing. And if you are watching this video and you learned U-substitution last year in AP Calculus, great. Hopefully this year it clicks for you even more. If you're learning this for the first time, just know that it is tricky, and the only way you're going to get good at it is through practice, is messing up and finding the wrong thing for you, realizing it's not going to work. You're going to get really good at deciding what you should be and proceeding from there. But you're going to make mistakes along the way, and that's part of the learning process. So my encouragement to you as always is to keep with it and always reach out if you need help. Practice, 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 and just keep at it because you're going to get it. You've got this.